Hi guys, welcome to today's lecture. This one is going to be a bit rough around the edges, seeing that I haven't gotten around to doing the editing yet. I want to quickly go through an example of a mass balance with chemical reaction to show you the differences between species balances, elemental balances, and using the chemical reaction to calculate the mass balances. In this example, we're going to look at the thermal decomposition of hydrous zincite according to the chemical reaction given below, in a process as illustrated by this flow diagram. The only thing we know from the system is that out of the system we have 100 kilograms made up out of 80 kilograms of zinc oxide, 10 kilograms of the hydrous zincite, and 10 kilograms of silica dioxide. And for my calculation, I've used the molar masses as indicated on the far right. For this problem, because I want to indicate the difference between a species and an elemental balance, I'm not going to spend time on calculating squiggly or the extent of reaction. I just want to show you how to use a species balance, elemental balance, and the chemical reaction to solve this specific problem. Looking at this problem, the first thing we should notice is that the silicon dioxide does not partake in the reaction, as described below the diagram. It is thus an inert component. So let's start by trying to solve this mass balance. If we look at the system, we can see that the only species coming in and leaving the system as the same species is the silicon dioxide. You could say that the hydrous zincite is coming in and leaving the system as well, but a large fraction of the hydrous zincite is converted into the CO2 and the water going out, and also the zinc oxide going out. Thus, when we're going to do a species balance, the easiest one to do would be for the silicon dioxide. And we can thus say that 10 kilograms of the silicon dioxide is going out, which meant 10 kilograms of the silicon dioxide came in. When we're going to do an elemental balance, we can now do a zinc elemental balance, a carbon elemental balance, an oxygen elemental balance, and a hydrogen elemental balance. But looking at this, it is clear that doing an oxygen elemental balance is not going to help us at all, seeing that there's some oxygen in the silicon dioxide as well, which we've already taken into account. And having a look at the O3 and O to the power of 6 here versus O2, O, and so forth going out, we can see that it's going to be quite a complex elemental balance. There's nothing wrong with doing it, but there's an easier one to do. And if we look at this, we have zinc here and we have zinc there. So only in 2 of the streams do we have zinc. So this will make it a much easier elemental balance to do. Let's thus start with a zinc elemental balance, where we have 80 kilograms of zinc oxide going out of the system, which is equal to 0.9830 kilomoles of zinc oxide going out, but also the same amount of kilomoles of zinc going out, seeing that 1 mole of zinc oxide contains 1 mole of zinc. But we also have zincite going out, which is 10 kilograms, and this is equal to 0.0182 kilomole of zincite out. And because we've got 5 moles of zinc in every mole of zincite, it is 0.0911 kilomoles of zinc out, and a total of 1.074 kilomoles of zinc in the outstream. Now, with 5 kilomoles of zinc per kilomole of zincite, and knowing that all the zinc out must be equal to the zinc in, we can calculate that 0.2148 kilomoles of zincite is coming in, and this is equal to 117.93 kilograms of zincite coming in. Now we could also have done this slightly different, still an elemental balance, but not doing it on a mole scale, doing it on a mass scale. And first we need to calculate how much zinc is going out, and this we could do by calculating the zinc out as zinc oxide. We do this by taking the zinc oxide out and multiplied by a ratio of the molar mass of the zinc to the molar mass of the zinc oxide. This basically gives us a percentage based on mass of zinc in zinc oxide. And to this we add the zinc in the hydrozinc site leaving the system. So we have the 10 kilos of hydrozinc site leaving the system multiplied by the molar mass of zinc in that stream. Remember, there's 5 moles for every mole of the hydrozinc site, divided by the molar mass of the zinc site itself. And we calculate that a total of 70.23 kilograms of zinc is leaving the combination of the zinc oxide and the hydrozinc site. And by using the molar mass of the zinc, we calculate that 1.04 kilomoles of zinc is going out. And we can see this is the same value as we calculated before. And in the same way we did before, we now calculate that 117.93 kilograms of zinc site is coming into the system. Now, to solve this problem, we can keep on doing elemental balances for the hydrogen and for the carbon, or for the oxygen, as we haven't used them yet. But there's a much easier way to solve this mass balance. Now, if we were going to use Quigley today, this is where we would have used it. We would have used it to calculate the extent of reaction for instance, the hydrozinc site, and then use that to calculate all the other components. I'm not going to do it this way. I'm going to do it in a much shorter way, but just as an example. This shorter way can always be used, but for bigger problems, it becomes troublesome and clumsy, and just using extent of reaction will be much easier. If I now take the mass of hydrozinc site in, I subtract the mass of hydrozinc site out, I get the mass of hydrozinc site reacted. And from this, I can calculate the kilomoles of hydrozinc site reacted. And by looking at the chemical reaction, we see that for every mole of hydrozinc site reacting, we have 2 moles of CO2 forming and 3 moles of water forming. And we thus form 0.3932 kilomoles of CO2, or 17.31 kilograms of CO2. And 0.5898 kilomoles of water, which is equal to 10.63 kilograms of water. And to check if we are right, let's look at everything going out. So it's the zinc oxide, the silicon dioxide, the hydrozinc site, the CO2 formed, and the water formed, giving us a total of 127.93 kilograms. Now what is going in? Which is the 10 kilograms of silicon dioxide and the 117.93 kilograms of zinc site. If we add this up, we get a total of 127.93 kilograms in. Now, if the kilograms in equals to the kilograms out, calculated separate for the mass balance, then we know we've done the correct mass balance. I really hope this video helps. See you again next time.